Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. On today's show, we'll give a preview of what we'll be learning in calculus this semester. Much of calculus involves three key areas, or a combination of these three. The idea of limits, tangent lines and slope, and area. First, let's discuss limits and area. 2,500 years ago, the Greeks studied the area of curved figures. They broke up polygons into triangles. For example, notice in the figures below that there's a triangle inside a circle, that there's a lot of the area of the circle is not taken up by the triangle. As we move to regular polygons with a greater number of sides, for example, the square, that takes up more of our circle. The hexagon takes up even more of our circle. The octagon takes up almost the entire circle, and in the 12-sided regular polygon, well, that you can hardly even see any of the pieces of the circle that are left. Can you find an expression for the area of an n-sided regular polygon inscribed in a circle? We'll derive this formula in class, as well as the formula for the circumscribed polygon. Later on in the course, we'll show that this area goes to the well-known pi r squared as the number of sides increases. Next, let's discuss the tangent line to a curve. In order to write the equation of a line, you either need to have the coordinates of 2 points on the line or the coordinates of 1 point and the slope of the line. So on the black curve, let's note the points A and B. The line segment from A to B is called a secant line. As the point B moves down on our curve towards C, we get a new secant line. And as the point moves further and further down the curve, we would end up with just a point at A. And the line going through that point at A in the direction of the secant lines as the other point on the secant line gets closer and closer to A, that's what we call the tangent line. So that's one of the key areas that we'll be discussing in the course. Now let's take a look at the concept of area. In the circle example earlier, we saw that the Greeks broke up polygons into triangles. Later on in this course, we'll find the area under a curve by breaking the area into rectangles that are approximately the height of the curve and letting the number of rectangles grow. So on the right, in the top figure, we have the curve y equals sine x, and we've drawn 4 rectangles underneath the curve, and these rectangles account for a fair fraction of the area under the curve, but they still leave a lot unaccounted for. As we increase the number of rectangles to 8, there's less of the area under the curve that's unaccounted for, and as we continue to increase the number of rectangles, we have a smaller and smaller amount of the area that's left unaccounted for. Now these three ideas, the ideas of limits, tangent lines and slope, and area, are key concepts in calculus, and almost everything that we do in the course will be related to one or more of these areas. It'll be a good idea to keep in mind the big picture, limits, tangent lines and slope, and area as we go through the course so that it doesn't seem like a bunch of disjointed, disconnected facts and problems that have no relationship to one another. Let's take a moment for some math culture. There was a mathematician who was showing off a new proof that she came up with to a large group of peers at a math convention. After she's gone through most of her proof, one of the mathematicians in the audience says, "Wait a minute, that's not true. I have a counterexample." She replies, "Well, that's okay. I have 2 proofs." Thank you for joining us today. Have a great day, and may the power of math be with you.